So, a hearty good morning to all of you, and welcome to this webinar on pre-ECM course for geotechnical engineers. So, my name is Chinmay Patnaik, and I'll be your host for this session. And today we're going to cover the topic of stress seepage coupled analysis of a 2D NATM tunnel. Where I'll tell you some brief overview about the FEM course, and then we'll go to the background description where I'll show you some brief methodology of the tunnel construction methods, and then we'll talk about the seepage into excavation boundary. In the analysis and output section, we will talk about the workflow process, the model design, the geometric design overview, the meshing and the loading cases, description of the seepage boundaries or the nodal heads, then the construction stage planning, and finally the results and the output tools. In the end, I'll show you the certification task where you have to generate the exact same model that will be shown in this session, and you have to analyze all the model stages. You have to compile the results and the images, and finally fill up the annexer, and certain guidelines will be issued about the submission task. Okay, so now we'll start with the course overview. So this course is an online certification program in computational geotechnics using the finite element method, that is the GTS NX. So here we are not going to talk about any other method, and we'll slowly introduce you some of the salient features of GTS and its use in the implementation for solutions for the civil engineering department. And all the sessions will have the nonlinear static process. So it is a more accurate way of depicting what exactly happens in the field, and you will be also shown the interpretation of the FEM analysis results like the contour plots or the graphical tools, charts, images, some stuff like that. And finally, the certification task is for all the participants, be it professionals or graduates, and that will be using MIDAS tools for getting success in geotechnical numerical methods. So I hope everyone is clear that why we are organizing these sessions. And with that being clear, we'll start with the background description of today's main agenda, that is the tunnel construction and the seepage into the tunnel construction boundaries. So in terms of the various tunnel construction fundamentals or the methods, the most predominant methods are the cut and cover tunneling method, the DNB or the drill and blast method, the TBM method, and the sequential excavation NATM method, and the jacked box method. So DNB tunnels and NATM tunnels are not too different from each other. Most are based on the quite similar methodology that you have to provide support as you move on with the progression of the excavations, and at the same time you assess the pre-existing conditions as well as the upcoming conditions from time to time. And we are not going to talk about the TBM method today. Instead, it will be covered in the very last session that will be happening in November. Now, the choice of tunneling method is dictated by a lot of factors, like the most important ones being the site prep time. So the drilling and blasting requires much lesser time. All you need is to set up the machines, and normally nowadays with tunneling being on the boom, so every tier B or even tier C cities are starting to get up with the subway systems. The firms like Sandvik, Epiroc, or P&H, they are very, or even Caterpillar. These companies are right now everywhere. So availability of machines like the driller, the scrapers, and the bolting equipments, and the LSDs and the LPDTs, they are actually not hard, but yes, they are a bit of a investment that you need, but that will be far lesser as compared to TBM, because the TBM needs a lot of prep time, so you have to create shafts and lower it down, so it takes around 3 to 12 months. For the excavation rate, TBM is much faster, but TBM is again valid until only a certain value of rock RMR. Beyond that, you need to go for drilling and blasting again. Yet TBM will be a faster excavation than the DNB. And in terms of tunnel shape, you can get a horseshoe tunnel shape in D and B, or any other shape that you require, but mostly with TBM it is round. Ground vibrations are high in drilling and blasting or NATM method, but low in TBM. That is why a lot of expertise or skilled engineers are required. Along with geotechnical engineers, you need to have acoustic engineers if you are creating a DNB tunnel in an urban area, because the vibrations due to blasting will be very, very high, along with the noise and the other parameters. And DNB depends on where you are doing it, but again, it certain countries might have some regulations about these kind of tunneling under the urban areas, but TBM is normally widely applicable. You can use it anywhere you want. And as I have mentioned, in terms of skilled labor, DNB requires a lot of engineers on site from time to time to assess the situation, and if required, relook at the construction process or the methodology. But with TBM, once it is the TBM is set, it keeps on going. And in terms of cost, TBM is the highest in terms of expenses. DNB is bit lesser. And in terms of other factors, the geology, geometry, and the environment or the project timeline, what kind of financial parameters are available, all this dictate the choice of the tunneling methods. So now we will start with the basic process of the DNB tunnels. So the method just starts with drilling, then it goes to loading, or by loading I mean the loading of the charges, or it can also be called as charging in the mining terminology. Then it goes to blasting. After blasting, the ventilation has to be done so that the fumes are released to the safe zone. Only then the workers can go in. Then LSD or LPDTs do the job of mucking. Then scaling is required so that whatever loose overhanging rocks are there on the walls or on the roof, they will be dislodged, and we are left with a profile that is ready for bolting and shotcreting. Then the bolting is done. Then again surveying is done, and after the surveying done, again the drilling starts, and this is a chain process. So for NATM tunnels or sequential excavation, there is a very prevalent methodology that is used. So the design philosophy is based on two parameters. That is the design criteria pertaining to the NATM technical requirements, which necessarily dictates the primary support, the final support, the monitoring systems, and the geometry size and the excavation pattern, and also the ground investigation. And then it comes to the external constraints, like the purpose of that tunnel, how long it's going to last, or for how long the tunnel is supposed to be used. Then the ground settlement, the environmental impact assessment, the safety and of the workers and the nearby areas, then the technology that is supposed to be used, and finally in the end the most important detail, that is the contractual and the financial obligations that are coming under the program. So that brings us to the main agenda of why seepage needs to be studied properly, because seepage might lead to flooding if the seepage is unchecked and it has not been planned properly. Flooding of the tunnel is a potentially deadly incident. It can also lead to weakening of the liners and the support systems, and sometimes can lead to even collapse too. And excessive leakage will lead to ground subsidence, which is exactly what happened here in Cologne, Germany, when they were building the subway lines and they were dewatering. So unfortunately, they had two pumps. One of the pumps failed, and when one of the pump failed, the other pump started slowly taking load until it got overload and overheated, and that's when the entire water it rushed in and the diaphragm wall failed, and that is what led to this unfortunate incident. These kind of incident has also happened in India when a TBM punctured an aquifer, and the entire ground started having very strong vibrations and people had to be evacuated. And the bad side of this issue is that the TBM can be trapped in the rubble, and this has actually happened in India and also in the US. Now, finally, some of you might have heard of the term called as mine inundation. Inundation is nothing but and excessive flooding of the mine. Mine inundation is one of the largest causes of death in the mining industry all over the world. Uh, a lot of countries where the coal mines are operated. Even in India, we had the most dangerous incident in mine inundation happened in a coal mine where unfortunately 345 people lost their lives in a single day. So that is why we can understand the gravity of the situation, that why it is very important to study the seepage into the tunnels. So in terms of the methodology, the workflow process will always remain the same. So if you have attended our previous webinars, this slide is the most common slide that you will find in all the webinars, because that is the only way you need to proceed. So you'll start with the geometry, then you go to the material properties, then you go to the definition of the element attributes, then you create the mesh, you define the loading and the boundary conditions, then you go towards the analysis or the problem solving, and finally you display the results. Okay, so next comes the numerical model design. Here our objectives will be to cover the geometric design pattern. We will add the structural elements. We will talk about the materials and meshing. The loading, groundwater and seepage boundary conditions will be described. And finally, we will shed a light on the analysis and results. In terms of the model layout and description, so the tunnel is actually being done in a medium rock, that is the siltstone. So where the E modulus is around, I assume 0.15 GPa, and the height of the tunnel is 10 meters, and the maximum dia is 13 meters. So with a tunnel this big, one can easily assume that it is a civil roadworks tunnel, because mining tunnels are normally not this big unless they are the main roadways. So we have for the support system a liner that is 35 centimeters thick, and the depth of the tunnel is around 11.5 meter from the surface. And for loading condition, we have only considered gravity and the additional loads imposed by the seepage water. For geometric modeling, we need to create the points, lines, and interconnections. Then we have to create the 2D faces. And this is a 2D model, so we don't need to create the solid, and the Boolean operations are not needed. And finally, the 2D face that you have created, you have to transfer that geometry into a finite element mesh, because that is what gets calculated. Okay. For loading options and boundary conditions, I have described that we will use the self-weight or gravity loading, and we will assign the roller boundaries on the sides. That means the boundaries are allowed to move, and the fixed boundaries on the bottom. Now coming to the most important and the new aspect for this model, that is the CPS boundary condition. So we'll assign a nodal head to both the edges, or the same place where the nodes are assigned the boundary conditions for the ground supports. This will indicate that the entire soil is submerged, and will assign a nodal head of 20 meters. That means beyond the height of 20 meters, the nodal head will be taken as 0. And then we'll assign a review boundary. Review boundary is nothing but the potential seepage phase from where the water will seep into the excavation. And then we will execute the seepage analysis and then the stress analysis. So for the construction stage description, we have 8 stages, and this is a stress seepage semi-coupled analysis. That means the every stress stage is preceded by a seepage stage, where the pore pressures and the stresses will be calculated based on the seepage data that was calculated on the previous stage. And this will also assess the flow conditions on the excavation boundary. And the liners are modeled as structural elements, so they're assumed to be impermeable. Now, if I just play this video, you will see the plan of the construction stages. So now we come to the displacements or the results. So this is how the total displacements will look like towards the progression of the model. Then for the liner, we get the axial loads and the bending moments. Finally, due to the seepage analysis, we will get the groundwater level, that is the initial groundwater level. So this is the 20-meter height. Then due to the upper excavation, you can see the groundwater level dropping. That means the water is actually flowing into the system. Then due to the lower excavation, the groundwater level dropping further down here, and the multi-step ISO, which will be shown in the model. Then the results export. So these are the displacements chart, or the Word file image can be exported. Like if you have the snip, you can directly export that into the Word file. You can also generate the 3D PDF based on whatever you require in terms of your results. So for the initial presentation, that was all I had. Now we will go to polls. So after the polls, we will slowly go towards the GTS NX program, where I'll show you how to create the model. So we will go to the polls now, and then we'll go towards the model. So I hope everyone enjoyed the first part of the session, that was the presentation. So as of now, we're going to conduct two polls. So I will sincerely request everyone that please answer the questions to the best of your abilities. It will help us design the future webinars so that it is more enjoyable for all the participants in here. So I'm going to start the first poll question, that is this one. So what kind of FEM program are you using in your project? GTS NX, Fluxus, the Geoscience suite, GeoStudio suite, or Rock Science, or none of these? It's also perfectly okay if you are new to numerical modeling. We can completely understand. I'll request all the participants to please answer the polls. So thank you very much for this poll. We're going to have one more poll now, and then we're going to go to the model. Okay. So this is the second poll that we have. So what kind of project are you doing most frequently? Is it excavation or slope stability or foundations or tunnels or dams? So I'll repeat the poll question. What kind of project are you doing more frequently? Excavation, slope stability check, pile raft foundation, tunnels or dams? So once again, thank you very much for the active participation in the polls. And towards the end of this session, we'll have two more polls. So as of now, I'm going to show you how to model the entire project. Okay. So let's just sit back, relax, and enjoy the model right now.
The broadcast is now starting. All attendees are in listen-only mode.
So now we start with the GTS NX program. So when you open up the GTS NX, it's supposed to look like this. So now what we're gonna do is we're gonna click here on the file. We go to new. So we'll wait, and initially it's gonna ask for the parameter settings. So we'll wait for that to load up. So here we just enter the model type as 2D, and it can be left blank. and we just keep the unit system like that. We press OK. So first we reset the grid size. I bring it down to 2 meters. I bring it to, let's say, 50. Okay. So I go to here, that is the tunnel section. I'll just redo this. I'll bring it to 1 meter, so it's a bit easier for us to notice where to save it. Okay. So in the tunnel type, we go to 3 center circle plus invert, and everything else we're gonna leave like that. We go to either screen snap, or you can just enter the value of section center as 0, comma 7, and we press apply. So there it is. This is our tunnel section. Now what we do is we press intersect, select all. Okay. So there it is. Our tunnel section is there. Next, what we're gonna do is we create a line. So this line will divide the tunnel into two parts. So what I do is I go to here, create line. There it is. So tunnel is not divided into two parts, the heading and the benching, or in our model we're gonna name it as upper excavation, lower excavation. Next, we create the model boundaries. So for that, just zoom it out and I switch off the grid. I go to rectangle. I put the location as minus 50 minus 45. Minus 45. Apply. And here I enter 170. Okay. So there it is. Our base of the model is complete. Now we just need to do is divide it into different sections. I go to line, I go to 2D, I enter the location as minus 50, 20, press apply. Then in the relative location, press 100, 0, apply. Similarly, we again input the location as now minus 50, minus 10, apply, 100, 0. Okay. So there it is, topsoil, our tunnel in siltstone, and finally sandstone on the bottom. What I do is I just go to intersect all of them. So there you see. I'll recommend all of you to keep a tab of the intersect section. So whenever you create lines and you want to join them, blindly use the intersect option. It will do the job for you. So now what I do is I create faces. I select the top one like this, apply. Bottom one like this, apply. Upper X, apply. Lower X, apply. Then for the siltstone, select the 4 and everything on the tunnel boundary like this. Okay. So there we have it. So if I just, what I do is I just select all, press right, click on the mouse and use random color. So you can see all the different faces that have been created have been assigned a random color now. So next what we do, so as I mentioned before, in the material section you will get your the properties will be predefined for you, but here I'll just show you how to define the material properties. I go to more column, I name it as top soil, enter this value as 75,000, unit weight dry is 20, Position ratio 0.2. KO will be manual. I noted as 0.5. Then I go to porous, saturated unit weight 22. And I go to nonlinear tab, enter the cohesion value as 10, friction angle 30 degrees. Okay, press OK. For the rest too, if you want, you can manually define it. But since I have built this model, so what I'll show you is how to import properties. So I go to a different model and I press OK. I import the siltstone, sandstone, and the lining properties. Press OK. For the siltstone, the E modulus is 1.5 E6, position ratio 0.25, unit weight 24 dry, and KO is manual 0.5. For porous, we go to 25. You can leave the unsaturated property, you don't need that for your model. For and the permeability coefficients 1E7 in either direction. The cohesion will be 120 and the friction angle being 42 degrees. Okay, now I go to sandstone. The E modulus being 2.5 E6 and dry unit weight 23, saturated 24. Again the same permeability 1E minus 7, cohesion 150, friction angle 43 degrees. And for the lining or the concrete, the E modulus will be 30 GPa, so that will be 3E7, and position ratio 0.15, unit weight will be 25. So if you switch on the structure tab, what happens is that then it is assumed as to be a structure, and then the material property will be impermeable. So this will form as the impermeable liner that we have, so we don't need to do anything else for the waterproofing for this particular model. Now for the properties, we need to create plane strain properties and beam properties. So I'll show you how to create the beam properties, and I'll import the plane strain properties. So I go to beam, I name it as lining. I go to section, it will be solid rectangular beam 30.35 or 350 mm or 35 centimeter. So this the coefficients will be automatically calculated by the software, and I press OK. Now for plane strain properties, you just go to 2D plane strain, right top soil. OK, apply. Then we go to silt stone, apply. Finally sandstone. So remember, when you enter the property, you also have to change the material property below. So, and without creating the material property, you can't create the property or the element attribute. So you have to create the material properties first. So with that being done, we'll go towards the specialized meshing that we have for the 2D models. So I just deactivate everything or the faces so that only the lines are visible. I'm going to change the background to a different color. So here you can change your backgrounds. I prefer this one. So now what I do is I go to size control. I select all the mesh in here or all the curves along the tunnel. I press 1 as the mesh size, press apply. Now for the other sections or the soil sections, select all the curves like this, and you will have to define the mesh size based on what is given on the tutorial. Here I just take as, let's say, 2 meters. Press OK. So our basic input is complete now. So what I will do is I'll go on create the 2D mesh for everything. Okay. So I go to 2D, I go to auto area, And before I mesh everything, I'll just let you all know that this is a different way of doing the tutorial model. And there is one more way of showing on how to build this exact same model in the tutorial. You can refer to either this video or the tutorial, you will get the exact same result. So don't worry about it. Okay. So I'll select a mesh inner domain. Here I go click on here, select higher order element and mid side nodes on the geometry. I select this one first. Sorry, my bad. I press OK. I select these two first, like this, and here I have to click the register each mesh set independently. So I take it as siltstone. Either you can do that or you can just do it like this. It is your choice, however you feel necessary. I note it as upper excavation, apply, lower excavation, apply, then the bottom will be sandstone, apply, top will be top layer or topsoil, apply, then I select all the four curves for the siltstone, outer periphery of the tunnel. Okay, siltstone, I name it as siltstone. Okay, press OK. So here, if you follow this, you'll see you will have an extra mesh set created here. Just have to delete it, and it is all done now. So I just go to mesh control and switch off the size control. Okay, here you can see your mesh is complete. So before that, you have to do certain elements parameters correlation. So I'll just show you how to do it. Go to parameters, go to 2D, go to change thesis. Here you can see the element coordinates. Okay, you see the top is in the y and the right on the right is the x direction or the horizontal. You see some are not aligned properly. So what you need to do is select all the elements and go to base element. You need to select one element where you can see it is correct or the CSS is correct and you press OK. So there you see now everything has been aligned properly. On the vertical you have the y direction, on the horizontal you have the x and the z direction. Okay, now you just switch it off. So second thing what we're going to do is we're going to switch this off and we're going to assign the liner properties. So we go to extract, select the edges of the upper boundary, we name it as upper lining, apply, then select the bottom edges, noted as lower lining. Okay, so upper lining, lower lining, clear everyone? So our basic mesh sets are complete, but we have to also see what is the element coordinates of the liners. We'll change the background to white now. I go to CSS. Okay, they have been aligned properly, so not a problem for us anymore. So now I go to mesh. So what I do is I go to static slope analysis. I go to constraints. So let's define the ground boundaries. I name it as ground fixity. Press apply. Okay, and I close it down. Next will be the loading condition, that is the self weight. So I just note it as SW or self weight, whatever you want. Okay, So this bottom thick red sign will be the sign that the self-weight is activated now. So next we'll go for the important part, that is the seepage boundaries. So for the seepage boundaries, I'll just first switch off the ground boundary. So it's a bit easier for me. Also switch off the loading condition. We go to seepage consolidation analysis. We give a nodal head of total 20 meters to both the edges. That means all the nodes on these two edges will have that. Okay, you can see it's a minor error in here. So what I do is I just zoom it in like this and like this. Okay, and I name it as GWL or whatever you want to give. Press OK. So this being done, now we need to assign the review boundary to the numerical model. So we again switch off the mesh, activate all the curves. It's a bit easier to do that on the curves. So we go to review boundary. So review boundary is nothing but it will just it is the potential phase where the seepage will happen. We go to edge, select the edge, and we name it as upper review. Apply. Similarly, the bottom edges, bottom review. Press OK. So your initial modeling is complete now. The CPS boundary conditions, the static boundary and loading conditions, everyone thing has been defined. So now we go and define the construction stage set. So for here, first I do is I click on pan option and pan the model to the right, and I select stage set. Here in the stage type, select stress seepage slope, and you can name it whatever you want, not a problem. If you double click on that, it will ask you for the construction stage definition. So in the bottom where you see this show data, here click on activate. It is easier to use it that way because it will show you what is activated, what is not activated. So the initial condition, I will name it as in situ, and the stage type will be the seepage type or the steady state seepage. That means the seepage is happening from the the entire ground is left on the virgin condition, and we just need to reevaluate whatever is the pre-existing stresses on the ground, or what kind of water level is there in the ground, and this will be used to calculate the stress in the next stress stage. So I press save. That is all. Then we press new. In the stage type, we select stress. We name it as initial stress. We activate the ground boundary condition and the self-weight loading condition, and we click on clear displacement. Then you press save. So the next stage will be seepage for the upper excavation. So I name it as water ingress upper X. Here I activate the upper review boundary and deactivate the upper excavation mesh, and I select the stage type to steady state. Okay, that means it's a seepage. So we have deactivated the mesh now, so that the seepage will happen through this particular boundary, and we press save. So based on that, we will have a new stage. We will see the stresses due to the excavation and the seepage into the model, and name it as upper excavation or upper X stress. The stage type will be stress, and we don't need to do anything because we have already deactivated the mesh there in the previous stage. So it will just calculate the stress in the ground right now. We press new one. We name it as upper lining. So here we activate the upper lining and press save. The next will be again a seepage stage where we will deactivate the upper review boundary because now we have the liner in there which is assumed to be impermeable. Therefore, we'll just activate the bottom review like this. We name it as water ingress lower X and we press save. Then we just have this repeat the same drill, that is stress stage, and we name it as lower X stress, press save. So here I forgot to mention two things. In the upper excavation stage, what we do is we activate the load distribution factor. That means what load will be taken by which element. So for this stage, I just delete that. For this stage, it will be 0.6. For the next, it will be 0.4. You have to do the exact same thing in the tutorial 2, and you press save. Now, in the lower excavation water ingress stage, you also have to deactivate the lower excavation so that the seepage will happen from the bottom now. We press save. And in the lower excavation stress stage, we again activate the LDF. I delete this. For this stage 0.6, next stage 0.4, press OK, save. Now finally we'll have the lining stage. Name it as lower lining. Here you just activate the lower lining and that's it. So our 8 stages are complete now and we just close it. Okay, then we close it down. If you go to stage set, you can see this is how it happens. So to create a new analysis case, you can go to analysis and go to general, or otherwise you can just go click on right click on the analysis case in here in the analysis tab, press add, solution type, construction stage, name it as SCL tunnel, and then go to the analysis control part. We do need to create an initial stage for the stress analysis, so that will be the initial stress. Activate the KO condition, activate the cutoff negative effective pressure. So this activate cutoff negative effective pressure is nothing but it just eliminates the tensional stresses that are created in the initial stage, because since the initial stage is the linear elastic stage, the stress calculation will be a bit higher and it might lead to failure in soil elements in the future stages. That is why we need to activate this one. We activate this and we activate save all stages, press OK, press OK. Now we just run the model. This is a very short model, so it will be done really fast. So then you need to just save it and name it as, whatever name you give, save. So now I'll share you the model results. So go to result. In the lower lining, the total displacement looks like this. It's in mm. You can change for meter to mm in here. Okay. Then the forces on the liners, the axial force. And I press on contour. So we just only see the forces like this. So we have both tensional and compressive forces on the beam elements. Then we go to bending moments. Then we go to any excavation stage. Look at the displacement. We switch on the contour now. So this is how it's going to look like. If I go for plastic status of the ground, go to plane strain stresses, go for plastic status. There is no plastic failure in the ground, which is a very good sign. And again, the entire model was done on a medium rock, so we didn't expect, any big failure to happen. And also with the ingress of water, you don't want any kind of plasticity to develop in the ground or in the rock, because it is a very clear indication that the entire thing might collapse and then it will get flooded. Collapsing of the tunnel is still okayish, but if the tunnel collapses leading to ingress of huge amount of water, it is potentially deadly for the entire vicinity. So if I go to phreatic line, this is how the phreatic line looks like in the low excavation water ingress. So check on flow rate is in cubic meter per second. I change it to centimeters per second. So the maximum flow rate is 0.27, that is flowing inside the tunnel. So if I calculate that and make it into per day, you will see the value will be actually quite big. If I go to calculator and I multiply 0.27277, 0. It will be quite big. So right now let's just skip this part, okay? And you can manually do that. So here you can see the maximum value that you are seeing. It's only positive. That means it's flowing into the system. And here it is negative. That means it's flowing out of the system. Okay. This is the pore pressure head. The pore pressure values. If I switch it back to meters, you go to pore pressure head, you can see the height of the phreatic line in piezometric heights. So remember, you have to check all of this in your tutorial file that will be given for the task. Now coming to the upper lining stage, this is how the displacements look like. Then the beam axial forces, bending moments. Okay. Then finally I go to the seepage stage in the water ingress or of the upper excavation. Switch on the contour. Phreatic line looks like this. Flow rate will be from the sides. So if I change it to centimeters or meters per second, you see it is quite high as compared to the second one. It is around minus 0.56 cubic centimeters per second. So that means it will be in a couple of liters per day. That means you have to install pumps in there in case if you have a tunnel project which is like this. This exact flow rate determination on the nodes is also a good area if you have a brief overview of your tunnel model and you want to see where to install this drainage. You have to you have to drill extra for drainage. You can actually assess from these CPS and coupled analysis modeling. Now I just change it back to meter, the units. Finally, we go to in situ conditions. Let's check for the phreatic line. This will be our phreatic line. There will be flow rate will be 0. Okay. So after this, I'll just show you a couple of things like how to create the multi-step ISO. So I go to multi-step ISO. I go to nodal CPS results in the data. Click pore pressure head. So you can see the pore pressure data changes from minus 15 meter to 65 meters. Here you have to enter the 0 value, that is the ISO line. Press plot. So you have to publish this snip on your result. Initial water level, phreatic line, the phreatic line due to upper excavation, phreatic line due to lower excavation. Okay. Similarly, if you want to get the charts, you can go to extract. Let's say you want to see the displacements. Go to SCL tunnel, results type, displacements, total translation. I want to see the absolute max. Go and it will be plotted in a table like this. I right click in here. I change it to normal numbers because I sometimes get confused with scientific numbers. So I'll be very happy to revert back to normal numbers. I go to millimeters. So select this one and this one, right click, show graph, press OK. So this is how you can create your graphs. And similarly, if you want to export your image file, what you can do is you can actually go to image file. Let's say I want to see this particular diagram. You can export it to Word or image, whatever you want. Press execute. It's loading right now, so we'll wait a couple of seconds and it's done. So whatever images you want to export in a Word file, they can be done easily like this. Okay. Don't want to save it, so I'll quit it like that. Press close. Now, so if you want to see the direction of movement, go to vectors. You can see there is squeezing in the tunnel. The invert is coming down and the bottom part is coming up for the vertical. And for the horizontal, it's kind of the same thing. Okay. The horizontal movement and the vertical movement. So if you want to see the minimum and the maximum, or you can have to, you want to create a boundary query, you can go to probe option, and whatever query you want to check, it can be seen in here. Let's say you want to see the displacement along each node. You can see the max and the min is already given here. Just select the node and it's gonna look like this. Okay. So if you want to see the safety factor values, press safety factor. You can see everywhere the safety factor is beyond 1, which is good, except at some points. So safety factor of exactly 1 or 1.1 means like some more support can be needed in there. So safety factor in GTS NX is not exactly the strength factor. So please take a note of that. It is nothing but the safety factor is the ratio between the existing stress on the ground versus the strength of the ground at that particular node. And it's based calculated on the Moore Coulomb strength criteria. And GTS does not have the strength factor option in here, but we are looking at that for the future developments. So this is how you can get your model results. Okay. And so I hope everyone enjoyed the GTS NX model right now. So next we're gonna conduct some polls and then we'll go to the certification task. Okay. So thank you.